Jai Hind. Myself Ravind Kumar, AP in Electrical Engineering Department, Ajakmar Garg Engineering College, Ghaziabad. Today I am presenting on the topic three-phase circuits, or that is three-phase supply system in the second unit, and that is AC circuits, and the subject is fundamentals of electrical engineering. And this subject is basically intended for first year students who are taking this course in the first year classes. So, in this topic of three-phase supply system or three-phase circuit, we will be discussing different subtopics that we can see here, like what are the advantages of three-phase supply that we will discuss here in this, how to generate three-phase supply, what is phase sequence in three-phase supply, what is balanced and unbalanced supply and the load, three-phase load, then the relation between line and phase quantities and power consumption in three-phase balance system. So, these are the various topics which will be discussed under this discussion today. So, first we go for the advantages of three-phase supply. So, if we see the advantage, these are the different points which are there. First advantage is that the amount of conducting material required to transfer a given amount of power is less in a three-phase system. The reason for this is when we supply the power in three-phase system at higher voltages, then the current required to supply this power will be smaller for a given amount of power. And when current is small, that means current, we know current is given by voltage upon resistance or impedance, whatever we take it. So, for smaller current, resistance will increase, that means current will go down. For higher voltage power supply in three phase, then resistance will increase, and resistance we know that is given by rho L upon A. So, with the increase in resistance, the area that will decrease, cross sectional area, and with the decrease in cross sectional area, that means we will require less conducting material in the three-phase supply system. Another advantage, three-phase supply is required by three-phase induction motor, which are widely used in the industries due to the ruggedness, longer life, higher torque, low initial and maintenance cost. They are all the advantages associated with the three-phase induction motor. That's why they are widely used in the industries, and these are used with three-phase supply. So, that is again an advantage associated with it. Another one is domestic as well as the industrial and commercial power that can be supplied from same three-phase distribution system. Since in distribution system we have three phases and one neutral. So, with the help of that we are able to supply three-phase power as well as single-phase power. Other than that, three-phase system has better voltage regulation, that is also the advantage of it, and for a given size of the machine, the power generated by three-phase alternator is higher in comparison to single-phase machine or single-phase generator, if we compare it with that. So, all these are the advantages which are associated with three-phase supply system. Other than that, how to generate three-phase supply? For this, what we do, we use three-phase AC generator, that is also known as alternator, three-phase alternator. So, there are three different phases like A1, A2, these are the terminals of phase A winding. Similarly, B1, B2, these are the terminals for phase B winding. C1, C2 are the terminals for phase C winding. So, that way these are the three phase windings for three different phases, and they are wound over a common rotating structure which is known as rotor, and when it is rotated in the magnetic field of stator, then variable flux that is linking with these three phase windings, and due to this variable flux linking with these three phase windings, EMFs are induced in these three phase windings or coils as per Faraday's laws of electromagnetic induction. and that way we are able to generate three-phase supply with the help of it. The expressions for this, the instantaneous value of voltage in phase A, that is given by small Va, and it is equal to Vmax sin omega t. Vm means maximum value of voltage generated in phase A, and in polar form it can be written Va equal to Vph magnitude angle 0. That means it is along reference. Since when we are using this sin omega t, there is no angle with omega t, so it will be along reference. That already we have discussed in the generation of EC initially in this second unit. Then phase B voltage, instantaneous value Vb, that will be given by Vm sin omega t minus 120. Vm is again the maximum value of voltage, and it is lagging by 120 degree angle from reference, and phase A is along reference, so phase B is lagging by 120 degree from phase A. That can also be said from this. And in polar form it is written as Vb equal to Vph magnitude angle minus 120. Similarly, for phase C, instantaneous value of the voltage is Vm sin omega t minus 240, or in polar form it is written as Vb equal to magnitude of Vph and angle minus 240. That means this phase C voltage, this is phase C basically, not Vb, this is Vc. So phase C voltage, that is lagging by 240 degree angle from reference, or we can also say phase C voltage is lagging by 240 degree from phase A voltage. In other words, that can also be said. And these are the waveforms representing these three phase voltages. Like this red color waveform, this is representing for phase A voltage. Then this blue color waveform, that is representing this phase B voltage, and green color waveform, that is representing phase C voltage. So if we see from this, phase A, that is starting from 0, so this is along reference. Then phase B, that is lagging by 120 degrees. So from this point to this point, there is a 120 degree phase difference. So phase B is lagging by 120 from phase A. Then phase C, this is starting from here, 0 point if we take it. So this is lagging by 240 degree from phase A. So that way these are the three different waveforms representing for three phase voltages for phase A, B and C. Vph, that is the magnitude of phase voltage, that is given by maximum value by root 2, since we are taking this phase voltage in terms of RMS value of the voltage. So that way these are the representations for three phase voltage waveforms generated in three phase supply system. Then next we have phase sequence. So these are the three phases Va, Vb and Vc, voltage of three phases. So phase A we are taking along reference, phase B lagging by 120 degree from reference, and phase C lagging by 120 degree from phase B, or lagging by 240 degree from phase A. Anyway we can write it, or we may also take it leading by 120 degree from phase A. So this sequence is known as phase sequence A, B, C. Now if we interchange any two phases one time, then this becomes negative phase sequence, like this ACB sequence. Here we are interchanging B and C together one time. So now phase A is along reference, phase C is lagging by 120 degree from phase A, while phase B is lagging by 120 degree now from phase C, or 240 degree from phase A. Or we can also say it is leading by 120 degree from phase A. So that way it is the reversal of phase sequence by interchanging any two phases one time. So here we are interchanging B and C together one time, that's why it is reversal of phase sequence. So that's why we can write it as that phase sequence can be changed or reversed by reversing the direction of rotation of the rotor of alternator. Since the rotor gets reverse rotation with the reversal of phase sequence, that way we get the reversal of phase sequence. And phase sequence can be defined as the order in which the three different phases they attain their maximum or minimum values, that is representing the phase sequence in three phase. Next we have balanced and unbalanced supply. So balanced supply means when all the three phases they have same magnitude, Va, Vb and Vc, the magnitude is equal, and angle between any two is 120 degree. That is balanced supply system. So, if the magnitude of three phase voltage they are equal and phase difference between any two is equal to 120 degree, that is balanced supply system. Now, out of these two conditions, if any or one of the condition is violated or both the conditions are violated, then the system becomes unbalanced three phase supply system. Like in this second case, in this diagram we can see this is unbalanced supply system, since the angle between any two phases that is different from 120 degree. Similarly, in this third case, that means in diagram C, angle is 120 degree between any two phases, but magnitude is not equal for phase A, B and C. That is why it is unbalanced supply system. And in fourth case, neither the magnitude nor the angle, they are satisfying the condition for balanced supply. That means the magnitude of three phases, they are not equal, they are different from each other. Other than that, the angle between any two phases, that is not equal to 120 degree. That is why this is also unbalanced supply system. So, second, third and fourth case, that is B, C and D, they are for unbalanced supply system. While first case, that is diagram A, that is representing balanced supply system. Next, similarly, we have balanced and unbalanced load in three phase. So, balanced load means when all the three phase impedances, they are of same nature and same magnitude, that is balanced supply system. But if any one condition is violated, that means the magnitude is not equal for this ZA, ZB and ZC, or nature is different from each other, then this becomes unbalanced three phase load. So, that is written here. If the three impedances connected either in star or in delta, they are equal, that means the magnitude is same plus nature is also same, then the three phase load is said to be balanced supply system, balanced load. While if load and supply are both balanced, then three phase system is said to be balanced. And if any one condition, that means the magnitude of ZA, ZB and ZC, that is not equal and or nature is not same, then it becomes unbalanced supply system. But unbalanced load, not supply, supply already we have discussed, this is unbalanced load. Under normal working condition, a three phase system can be taken as balanced supply, balanced system, in terms of balanced supply and in terms of balanced load also. This is star connection of three phases and this is delta connection of three phases. That way we take star and delta connection for three phase system. Next we have some quantities which are used in three phase system like voltage and current we are using in power system. So, in three phase system, line voltage that can be represented as VL, L represents for line. So, this is the voltage between the two lines. Similarly, the another term is phase voltage, that is VPH, PH represents phase and V is for voltage, so that is why VPH is phase voltage. This is the voltage between a line and neutral, or we can also say it is the voltage of a phase with respect to neutral. So, this is the way to represent phase voltage and line voltage in the three phase system. Next, we can establish the relation between line voltage and phase voltage in the three phase system for star connection as well as for delta connection. Like here, this is three phase star connection. This is three phase star connection. Star is represented by Y, since the shape is similar to Y. So, that is why we write it Y or star. So, here these three phases, voltages of three phase VAN, VBN and VCN. These are three phase voltage and they are connected in star, this is neutral point or star point of star connection. So VAN, VBN and VCN, they represent phase voltages of three respective phases, while VAB, VBC and VCA, these are the line voltages, since these are the voltages between any two lines or between any two phases. That's why VAB, VBC and VCA, they represent line voltages. And this is the phasor diagram which is representing phase voltage and line voltage, like VN, that is along reference, VBN is lagging by 120 degree from VN and VCN is lagging by 120 degree from VBN, or it is lagging by 240 degree from VAN under balanced supply system. And also the magnitude of VAN, VBN and VCN, they will be equal under balanced supply system. So from this we can find line voltage, that what will be the line voltage like VAB, the value of it, or VBC or VCA, which are the line voltages. We can find these three line voltage in terms of phase voltage, or we can establish the relation between line voltage and phase voltage from this. So when supply is balanced, then the magnitude of these three line voltages VAB, VBC and VCA, they will be equal, and that is equal to root 3 VPH. That can be found from this phasor diagram. We can see it, how it is found. And when the phase sequence is ABC, which we have taken here, that time VAB leads VAN by 30 degree, VBC leads VBN by 30 degree and VCA leads VCN by 30 degree. So how can we find it? We can see it. For this, suppose we want to find VAB, which is line voltage between A and B. That can be written VAN minus VBN, or that can also be written as VAN plus VBN. So, plus VNB, not VBN, this is VNB. We can reverse the order. So from this phasor diagram, if we say it, this is VN, this is VBN. Now we are to take reverse phasor of this VBN, so that we get minus of VBN here. So this is reversal of VBN. So this becomes V and B. This dotted line, that is representing V and B. And this angle is 120 degree between VN and VBN, that already we know. So now when we are taking reversal of this phasor VBN, which is now VNB, this angle becomes 60 degree between VNB and VAN. So now the resultant of VAN and VNB, that will become line voltage VAB, that is from this relation. So if we find it, we can find it using parallelogram method. This is the parallelogram, which is this line, this line, this line and this line, that is representing this parallelogram. From this we find VAB. So VAB will be given by under root of VAN square plus VNB square plus twice of VAN into VNB cos 60. Since the angle between VAN and VNB is 60 degree only, and VAN and VNB, they are phase voltage. So we can write it VPH square plus VPH square plus twice VPH square into 1 by 2, since cos 60 is 1 by 2, and from this it comes out as root 3 into VPH. So that way we find this relation in this star connected system, that line voltage is root 3 times of phase voltage. That is the way to find it, or way to derive it. Now next we have line and phase current in 3-phase circuit. So this is 3-phase star connected circuit, this is 3-phase delta connected circuit. So here in case of star connection, this is the line current, and the current here in this, that will be phase current. So from this, if we say it, line current and phase current will be equal. This is line current. current flowing through each impedance is called phase current, and current flowing through each supply line is called line current. So this is line current here. This is line current, line current. Similarly here this is line current, line current, line current, and this is the phase current. Similarly here it is phase current. Here it is phase current. And same way this IAB, IBC and ICA, they are phase currents. So we can find the relation like in star connection, this is line current equal to phase current, reason being whatever is the current passing through this line, same current is going in this phase also. That's why these two currents, line current and phase current, are equal in star connection. But in delta connection, line current and phase current are not equal, since this current which is passing through this line, that is distributed in this phase and in this phase. So that way this line current cannot be equal to phase current in delta connected system. We will establish the relation for this, and this is the phasor diagram representing phase voltage and phase current. Similarly, line voltage and line current, all these quantities, they are represented in this phasor diagram. Load we can take either star connected or delta connected, anyway it may be there, that may be the type of load connected as shown in these two diagrams. Now, if we find this relation between line and phase current, like we have found this for line and phase voltage, in star connected load, line current is equal to phase current, that already we have seen in this previous slide, that line current and phase current are equal. But in delta connected system, line current and phase current are not equal. In delta connected system, the line current is given by 2 into phase current into cos 30, or this can be written as root 3 into phase current. Since cos 30 is root 3 by 2, so 2 into cos 30 becomes root 3, and IAB, that is phase current. So we can write line current equal to root 3 into phase current, or this can be represented as root 3 into V upon Z, where V is phase voltage and Z is the phase impedance. So ratio of phase voltage to phase impedance, that is phase current, and this is equal to IB magnitude or IC magnitude. So IA, IB and IC, they are representing line current. This can also be written as IL, line current. And in a balanced delta connected load, 3-phase load, line current becomes root 3 into phase current, and phase current is given by this. So that way we establish the relation between line current and phase current in delta connected load. Next we have power in the 3-phase load or 3-phase system. So this is representing 3-phase system. These are the 3 phases A, B and C. See, this is balanced 3-phase supply system, and these are the 3-phase load impedances Z, Z and Z. All these are equal magnitude impedances and of same nature impedances. So that way it is 3-phase balanced supply and 3-phase balanced load system. So the total power consumed by the load, that will be given by 3 times of power in any one phase. P is the 3-phase power. This is 3-phase power. We can write it 3-phase power. This will be 3 times of power in any one phase. Reason being, all the 3 phases are in balanced condition. So the 3-phase voltages will be of same magnitude. Angle between any two will be 120 degree. Similarly, 3-phase currents will be of same magnitude, and angle between any 2-phase current will be 120 degree. So that is balanced system. So that's why whatever is the power taken by one phase, that same power will be taken by all the 3 different phases. So the 3-phase power will become 3 times of any one phase power, and this can be written as 3 into phase voltage of that one phase into phase current of that one phase and into the power factor. Cos phi represents power factor, and now it can be written as root 3 into root 3 VPH IPH cos phi, and we know root 3 into VPH, that is VL, line voltage, and IPH equal to IL in a star connected load. So that's why 3-phase power will become root 3 into line voltage into line current into power factor. And same will be the expression for 3-phase power in delta connected load also. Since in delta connected load VPH equal to VL we know, and IL equal to root 3 into IPH. So, if we simplify this expression for delta connected load, that time VPH will be equal to VL there, but root 3 into IPH will become IL there, and that is why the expression will again become same, that 3-phase power will become root 3 into line voltage VL into line current IL into power factor cos phi. So, that way this becomes the expression for 3-phase power in the 3-phase system. So, that is all about this, these various relations we have established in this. In the next lecture class, we will be discussing next topic. Thanks for this.